Welcome to Lecture 20 of Electrical Engineering 525. In this lecture, we will consider a modified version of problem 8.4-1. In this problem, the problem will read as follows. Two collinear half-wave dipoles are spaced a half wavelength apart, but not quite touching, and have the same amplitude and phase terminal currents. Calculate and plot the element pattern, the array factor, and the complete array pattern. So let's see how we would do this problem. The first thing that I want to call your attention to is that what makes this problem different from some of our previous problems is that we have half-wave dipoles. Now the terminology collinear means that these two dipoles are oriented along one and the same line. In this case, that is the z-axis. So these two dipoles are both along the z-axis, and since they are half-wave dipoles and are also only a half wavelength apart, they are almost touching each other, but we're told not quite touching. And furthermore, again, the terminal currents on these half-wave dipoles have the same amplitude and the same phase. Now, for a half-wave dipole along the z-axis, if that is the element, as is the case for this array, then the element pattern is given by this formula here. Ga of theta is equal to cosine of pi over 2 cosine theta divided by sine theta. This is a formula we've seen before, and as we have done before, I'll note again that this is independent of phi. Since we're talking here about a dipole that is lying along the z-axis, if you moved around this at some constant distance, you would see that the pattern does not vary in phi. So that's why we see no phi variation in this function. Now, we don't need this additional note for this problem, but we will need it for lecture 21. So let me go ahead and call your attention to another point here, which is that if we had a half wavelength dipole that was parallel to the x-axis instead of being parallel to the z-axis, then the element pattern, it would have a similar form to this, cosine pi over 2 cosine gamma divided by sine gamma, where gamma would be the angle with respect to the positive x-axis, just as up here theta is the angle with respect to the positive z-axis. Well, it's customary to write these patterns in terms of theta and phi, where theta and phi are the customary spherical angles, or angles of the spherical coordinate system. Gamma is not one of those angles, but we can express cosine gamma and sine gamma in terms of theta and phi in the following way. Cosine gamma is equal to sine theta cosine phi, and sine of gamma, of course, is square root of 1 minus cosine squared gamma, so that would end up being square root of 1 minus sine squared theta cosine squared phi. So when we substitute this expression for cosine gamma and this expression for sine gamma into our expression here for the element pattern for a half wavelength dipole parallel to the x-axis, we will get this final result right here. And once again, and notice that this pattern is a function of both theta and phi. Unlike the previous element pattern here for the dipole, half-wavelength dipole along the z-axis, which has an element pattern that's only a function of theta and is independent of phi. And once again, now we don't need this information for lecture 20, but in lecture 21 it is this will be an essential formula that we will need. So returning now to the problem under consideration, we have here the element pattern for this problem, and now we want to know the array factor. Well, recall that our universal array factor formula is given by this, and n is the number of elements, and psi is equal to beta d cosine theta plus alpha, where alpha is equal to minus beta d cosine theta naught. And remember that alpha is also the phase difference between any two consecutive elements in the array. Well, in this case, the array only has two elements, and the phase difference between them, remember we were told that the terminal currents have the same amplitude in the same phase, so the phase difference is 0 radians, and therefore alpha is 0 radians. So we can substitute that into this equation, and we get minus beta d cosine theta naught is equal to 0, which means that theta naught is equal to 90 degrees. So this is a broadside array. It should have its, when we plot the final pattern, we should have, well, even for the array factor, it should have the main beam in the direction of 90 degrees. And then we will see that for this case that the element pattern is such that the complete pattern will also have main beam in the direction of 90 degrees. But again, let me emphasize here that the fact that alpha is equal to 0 radians means that minus beta d cosine theta naught is 0, which means that theta naught is 90 degrees. So this information here only indicates what's going on with the array factor, and it has nothing to do yet. We don't have any further information. Let's say we're not factoring in anything about the element pattern. So this is just telling us that the maximum of the array pattern should be in the direction of 90 degrees. It doesn't tell us anything about where we should have the maximum of the element pattern. We'll get to that in a moment. Okay, so returning then, as we said before, psi is equal to beta d cosine theta plus alpha, and alpha in this case is 0, so that's psi equals beta d cosine theta plus 0, or beta d cosine theta, and of course beta is 2 pi over lambda, and d, the spacing between the dipoles, was half a wavelength, so that's lambda over 2, and so beta d cosine theta is the same thing as pi cosine theta. So now since we have this expression for psi is equal to pi cosine theta, that we're ready to substitute that back into this formula for f and find a final expression for f in terms of theta rather than in terms of psi. So what we will get here then, if we substitute psi is equal to pi cosine theta, well here, before we substitute for that, we'll have f of psi is equal to sine of, now here, this is the formula from above, it's this formula, but going ahead and substituting n equals 2, since the current or the array under consideration has only 2 elements, if we do that, then for our expression for f of c is sine of 2 c over 2 divided by 2 sine of c over 2. And remember that the sine of twice an angle is 2 times the sine of the angle times the cosine of the angle, so we get that in the top and 2 sine c over 2 in the bottom. And of course the denominator will cancel the first part of the numerator, and we're just left with cosine of c over 2. So f, written in terms of c, is equal to cosine of c over 2, but since c is pi cosine theta, then when we write f in terms of theta, we have f of theta is equal to cosine of pi over 2 cosine theta. Now if we want to go ahead and construct the plots, remember that for the plots, our polar plot will go from alpha minus beta d to alpha plus beta d. Now we've already found, as we've already said, alpha is 0, and beta d is 2 pi over lambda times lambda over 2, so that's just pi. So we're going to have a polar plot from 0 minus pi to 0 plus pi, or in other words, from minus pi to pi. So let's first plot the magnitude of f of c, the universal array factor, over that region. Well, as we've already said, f of c is cosine of c over 2, so when we plot that from minus pi to pi, we will get this plot right here. Now, if we let's come below to write the draw the figure, the polar plot for f of theta. Now, since the magnitude of f is equal to 1 here in the center, then the polar plot will touch the polar plot will touch the very edge of the circle here at this angle. And on the other hand, since this plot up here goes to 0 at minus pi and pi, then when we come down to those angles, this plot will go to 0. You see, either way, for either here at theta equals 0 degrees, or here at theta equals 180 degrees, the magnitude is 0. And so, as predicted, we see that the polar plot for f has a maximum at 90 degrees. Now, this is the array factor, array pattern. And now the element pattern, again, as we said before, that is cosine of pi over 2 cosine theta over sine theta. This is a pattern we've drawn previously in this course, and it looks like this. So these two curves, or two polar plots, look pretty similar to each other, and when we multiply them together, we will get the complete pattern shown here, which will be a bit thinner than either one of them, but like both of them, it will have a maximum at 90 degrees. And the expression for the complete pattern is obtained by simply multiplying the expression GA of theta here by the expression f of theta right here. So we end up getting f of theta phi equals cosine squared of pi over 2 cosine theta divided by sine theta. And you could verify, well, at 0 or 180, let's see how this would go. At 0, at 0 and 180, at those two angles, we would need to use L'Hopital's rule. But if we did, we would see that this is equal to 0, at either of those angles. And then at pi over 2, cosine of pi over 2 is 0, and so we'd have cosine squared of 0, which is 1 in the top. Sine of pi over 2 is 1 in the bottom. So sure enough, it's clear that at theta equals pi over 2, this has a magnitude of 1. And as I said, you could use L'Hopital's rule to verify that at theta equals 0 degrees or 180 degrees, the magnitude is 0. So the two questions I would like to ask about this are, what is the magnitude of f at theta equals 80 degrees and phi equals 0 degrees? Now, again, you can see that this function is independent of phi, so really it wouldn't matter what phi we specified here, but I'll just go ahead and specify phi equals 0 degrees. So if we wanted to know the magnitude at theta equals 80 degrees, of course we just plug in theta equals 80 degrees and we would get this expression 0.942. And then suppose we were asked to find the largest angle theta in the range between 0 and 90 degrees, such that f of theta and phi equals 0 degrees is equal to 0. Well, just take the expression that we have here for f of theta and phi, take the magnitude of that, because we're asked to find the angle that will make the magnitude equal 0. So magnitude of that is equal to the magnitude of cosine squared pi over 2 cosine theta over sine theta, and we're going to set that to equal to 0 and solve for theta. And that's pretty simple. That means that the numerator must go to 0. So and the numerator is cosine squared pi over 2 cosine theta. So take the square root of both sides, and we have this. And so the cosine goes to 0 at pi over 2. So we that means that pi over 2 cosine theta must be pi over 2, which means that cosine theta is 1, or theta is equal to 0 degrees. So that would be the only angle in the range between 0 and 90 degrees where the magnitude would go to 0. Now actually, I guess if you wanted to be real picky, you probably, in fact, I guess it really is, be careful. We notice when we say that the magnitude goes to 0 at 0 degrees, we didn't really check here, because the denominator would go to 0 at that point too. So let's go ahead and verify. I've made the claim twice that the function really does go to 0 when we at that angle. So let's make sure that's true. So let's take a moment to verify that. So if we use L'Hopital's rule, it says that f of theta equals 0 degrees, phi equals 0 degrees, is equal to the limit as theta goes to 0 degrees. And I'm just looking at f now. Let's see. I'm not worrying too much about that magnitude at the moment. And that this is capital F. Okay, so now let's take the derivative of what we have in the top and the derivative of what we have in the bottom and see how this turns out. So in the top we have cosine squared of pi over 2 cosine theta. So if we take the derivative of that, we'll get 2 cosine, of pi over 2 cosine theta. Okay, because this has a form basically u to the n, where u is the cosine of pi over 2